Let's talk about the alternator. It is, without a doubt, the electromechanical heart of any modern vehicle's electrical system. Without it, the battery and every single electronic module are just running on borrowed time.
So, in this explainer, we are going to take a full engineering-level deep dive into the automotive alternator. We're going to blow past the basics and really dissect this thing as a complete system, from its core operating principles all the way through to advanced real-world diagnostic procedures.
We've broken down our analysis into 5 key sections. First, we'll start with the physics of how we generate power. Then, we'll look at how that power is converted and controlled. After that, it's onto the mechanical systems. Then we'll integrate it all into the complete vehicle circuit, and we'll wrap up with the professional diagnostic methods you absolutely need to know.
Okay, let's get right into it, starting with the fundamental principle of operation, electromagnetic induction. This is the foundation that the entire system is built on.
This right here. This is the law of physics that makes the entire charging system possible. It's the core mechanism that lets the alternator take the engine's mechanical, rotational energy and transform it into the electrical potential we call voltage.
Now, what's really interesting here is the design, the common Lundell-Clawpole rotor. You see, a single field winding gets energized, and that magnetizes 2 interleaved iron cores. These create a series of alternating north and south magnetic poles. As this whole assembly spins inside the stationary stator, its powerful magnetic field slices across the stator's 3 separate windings, inducing a 3-phase AC voltage, with each phase perfectly offset from the others by 120 degrees. It's a really elegant piece of engineering.
So the crucial point here is the electrical integrity of these windings. For the rotor's single field winding, you absolutely must measure between 2.5 and 5.0 ohms right across its slip rings. Why? Well, that resistance is critical because it dictates the field current draw. Now, for the stator, which is built on a laminated iron core, the resistance between any 2 of its 3 output leads has to be incredibly low. We're talking between 0.1 and 0.3 ohms. Any measurement outside these specific ranges points to a definitive internal fault. No ambiguity.
Generating 3-phase AC is a great start, but it's not what the vehicle can use. The electrical system needs stable, direct current. So this section is all about the conversion and control process.
And this gives us a fantastic look at the full-wave bridge rectifier. It's made up of 6 diodes. You've got 3 on a positive heatsink and 3 on a negative one. Through a process called commutation, which is basically a high-speed electronic steering of the current, these diodes conduct in a precise sequence. The result? They convert that 3-phase AC into a single pulsating DC output. And remember, each diode that's conducting has a forward bias voltage drop of about 0.5 to 0.7 volts.
Now, here's a key diagnostic signature. If you have a failed diode inside that rectifier bridge, you'll get excessive AC ripple voltage at the battery terminals. If a diode fails open or it shorts out, some of that AC voltage is going to leak into the DC system. The spec here is absolute. AC ripple cannot exceed 400 millivolts. That's your pass-fail line.
If the alternator is the heart, the voltage regulator is absolutely the brain. Its entire job is to modulate the current being supplied to the rotor's field winding. It does this using something called pulse width modulation. A transistor basically flicks the field circuit on and off incredibly fast, adjusting the on time, or what we call the duty cycle. This gives it precise control over the strength of the rotor's magnetic field, and therefore the alternator's voltage output. It keeps things stable no matter the engine speed or electrical load. And of course, modern regulators are incredibly sophisticated. They use temperature compensation logic, so they'll raise the target voltage to around 14.8 volts when it's cold to help overcome the battery's increased internal resistance. Then, they'll lower it to about 13.5 volts when it's hot to prevent overcharging. In the really advanced smart charge systems, the engine control module talks directly to the regulator over a LIN bus network. That's a dedicated communication line. The ECM can command a specific target voltage and monitor the alternator's duty cycle and any fault status in real time.
Okay, let's connect the electrical to the physical. We're going to move to the mechanical components, because as you're about to see, the best electrical performance in the world doesn't mean a thing if the mechanical side isn't holding up.
Okay, 3 critical components here. First, current gets delivered to that spinning rotor field coil by 2 carbon brushes riding on copper slip rings. These brushes are a primary wear item. They start out at maybe 15 to 20 millimeters new, and they're done at a 5 millimeter threshold. Next, the rotor is supported by 2 high-speed bearings, designed for speeds up to 14,000 RPM. When these fail, you'll hear a very distinct RPM proportional whine. And finally, many modern alternators use an overrunning alternator decoupler pulley, or OAD. This thing contains a one-way clutch and a torsional spring to absorb crankshaft speed changes. If an OAD fails, it'll just freewheel in both directions, and the belt can't turn the rotor at all.
All right, now let's trace the path of current flow through the entire charging circuit. We're going to analyze all the critical connections, from the alternator's B-positive terminal all the way back to chassis ground.
So, the high amperage current flows from the alternator's main B-positive output stud through a heavy gauge cable that's protected by a fusible link. From there, it goes to the battery's positive terminal and the main power distribution module. But, and this is so important, the return path is equally critical. Current has to flow through the alternator housing to the engine block and then back to the battery's negative terminal via a main engine-to-chassis ground strap.
This right here is a fundamental diagnostic principle that you have to understand. Excessive resistance from something as simple as corrosion or a loose connection creates a voltage drop, and that can happen on either the positive or the negative side of the circuit. This is exactly why a methodical voltage drop test is an absolutely non-negotiable step before you even think about condemning an alternator.
All right, we have the theory down cold. Now, let's put it to work. This section covers the essential professional diagnostic procedures, complete with the explicit pass-fail criteria you need to know to do the job right.
This first test gives you a rapid and incredibly accurate assessment. Get the engine to 2,000 RPM with the accessories off. Your DC voltage should be stable, somewhere between 13.5 and 14.8 volts. That confirms the regulator is functioning. Then, you switch your meter over to AC millivolts. The reading must be below 400 millivolts. Anything higher tells you you've got a failed rectifier diode. It's that simple.
Now, to test the circuit's integrity, you're going to connect your voltmeter across the main charging cable. That means one lead on the alternator B-positive stud, the other on the battery positive post. With the engine running and all the electrical loads you can find turned on, the voltage reading has to be less than 0.2 volts. A higher reading means you have excessive resistance that you have to find and correct. And don't forget to perform the exact same test on the ground side.
And here's something really important to keep in mind. Alternators are not perfectly efficient, not even close. The conversion from mechanical to electrical energy is typically only 50 to 65% efficient. The rest is just lost as heat. This creates a really significant parasitic load on the engine. As a rule of thumb, for every 10 amps of current output, the alternator is consuming roughly 1 horsepower.
To make sure you get a lasting repair, you need to stick to these service details. Always torque the B-positive output nut to the manufacturer's spec. This prevents a high-resistance connection from developing later on. It's also best practice to replace the OAD pulley anytime you put on a new alternator. It just protects the new unit's front bearing from damage. And of course, always verify these key electrical specs on the bench before you even think about installation.
Look, a methodical, systems-level understanding is the absolute key to an accurate diagnosis. It allows us to move beyond just swapping components and hoping for the best, and instead to really address the root cause of charging system failures, whether that fault lies inside the alternator itself or in the circuit that's supposed to be supporting it.